In this video, I'm going to talk about inverse functions and how to find an inverse function, and then kind of the relationship between the two once you have the inverse of a function. Okay, so there's going to be a four-step approach that we take in order to find the inverse of a function. So the four steps are going to be, we're going to exchange f of x for y, and then we're going to swap x and y, which means x becomes y and y becomes x. Then we're going to solve for y, and we're going to exchange y for this little notation here that kind of looks like f of x, but it's got this little exponent of -1 up there. It just means the inverse of a function. So the first function we're going to look at is f of x equals 2x plus 5. So the first step we need to take is to exchange the f of x for y. So instead of f of x, I'm going to put y equals 2x plus 5. Okay, now the second step says to swap x and y. So y becomes x, and x becomes y. And we're going to discuss here in a moment why this has to happen and what happens because this happens. Okay, so the third one is to then solve for y. Okay, so if we're going to solve for y, we need to isolate this y. So we're going to start by subtracting 5 from both sides. So on the right side we have 2y. On the left side we have x minus 5. And then we can either divide both sides by 2 or divide every term by 2. They do the same thing. So this will end up being like 1/2 x minus 5/2. And you can even turn this around if you want to make this y equals 1/2 x minus 5/2. So the last step that we're going to do is that we're going to exchange y for this notation that means the inverse. Okay, so this y gets exchanged, and we read this the inverse of f. Okay, so we have that right here. Let's take a look at the graph of what this might look like. Okay, so when you look at this graph, you've got three things going on here. In the black, you have the original function. In the red, you have the inverse of that function, and then you have a green dashed line that kind of separates them, it looks like, and that's going to be y equals x. So why do the graphs look this way? Kind of why are they oriented around the line y equals x? Because remember in step 2, when we were finding the inverse of a function, we swapped the x and the y. So the x became y and the y became x. So that means that all the ordered pairs that satisfied the original function got flipped. So all the y's now are x's and all the x's are now y's. So what that does is that basically moves the line across y equals x. So then the new line, which is the inverse, the red one, it is now symmetric to the original function about the line y equals x, simply because all the ordered pairs flip from x to y and y to x. So for example, if you look and see, we have the point 0, 5 on the original function. So if you switch 0, 5 around, you'll get 5, 0. Well, if you go to the red line, you'll look that 5, 0 is indeed an ordered pair that satisfies the inverse. So just remember when you're doing this, that the inverse will always be symmetric about the line y equals x with the original function, and it's just that all the ordered pairs got flip-flopped. X became y, y became x. So in the second example, we're going to look at f of x equals, we have the square root here, square root of the quantity x minus 5. So if we follow our steps here, the first step is going to be to exchange the f of x for y. So I'm just going to write y equals, and that square root quantity from the right side. Okay, then we're going to swap the x and y. And again, as we just kind of discussed, swapping this x and the y will turn that line. The inverse will be symmetric about the line y equals x, because all the y coordinates became the inverse's x coordinates, and all the original x coordinates became the inverse's y coordinates. So every ordered pair just gets flipped. Okay, so after we swapped x and y, we're going to solve for y. Sometimes this can be a little challenging if you have a lot going on. In our case, we have a square root here of all this business. So we want to isolate this y, so we need to get rid of the radical, and we need to get rid of the 5. So I can use the squaring property here of equality, and if I square the left, I can square the right, and everything stays nice and equal. So I have x squared over here on the left, And on the right, my square root and my square cancel out, and that releases my y minus 5 from being bound in that square root. So now I have x squared equals y minus 5. So I can add 5 to both sides, and I'm going to get y equals, and it'll be x squared plus 5. Or, of course, I can flip it around and say y equals the x squared plus 5 this way, using the symmetric property of equality. And then our final step is to exchange y for this notation that means the inverse. So we'll say the inverse function is x squared plus 5, just like that. So we're just following that 4-step approach, and let's take a look at the graph. On this graph, you'll notice that our original function, the square root function, is in black, and it's in the lower right-hand corner. And its inverse, which is in red, is going to be across the line y equals x, which is our green dash line again. So notice that I have broken up the parabola, which is our inverse function, into a dashed part and a solid part. I did that only to show you kind of a graphical representation of how the function and its inverse are symmetric about the line y equals x. While the inverse of the function is the entire parabola, we can notice that only the right side of that parabola, which I left solid, is going to be the symmetric part about the line y equals x, and the dashed line doesn't have a reflection because the square root function doesn't reflect itself over the x-axis like a parabola reflects itself over the y-axis. So anyway, so here's the functions graphed, so you can get a graphical representation of what's going on there. In this third and final example, we're going to look at the function f of x equals, and we're going to have 1/2 x cubed minus 1. So if we go back to our 4 steps, to find an inverse function, the first one is to exchange f of x for y. So we'll write this as y equals 1/2 x cubed minus 1. And then the second step says to just swap the x and y. And again, we've discussed a couple of times now what happens when we do that. So we have x equals 1/2 y cubed minus 1. And then number 3 is to solve for that y. Okay, so when we're solving for y here, we want to isolate this y. We got this minus 1 and this 1/2 and this cubed right here that's kind of keeping y from being by itself. So we can step through and go one thing at a time. The first one is going to add 1 to both sides, so that addition property of equality. So I'll have x plus 1 equals the 1/2 y cubed. And then I can multiply both sides by 2. The reason is to get rid of that 1/2. So now I have 2 times the quantity, x plus 1, which I think I'll go ahead and multiply out 2x plus 2. And then we have that equals y cubed. So what do we do to both sides to get rid of this y cubed? Well, we take the cubed root, because then the cubed and the cubed root cancel each other out, and we're left with y. So on the left side, we have the cubed root of 2x plus 2 equals y. So of course, we can flip that around and say y equals the cubed root of 2x plus 2. And once we've solved for that, then the last step then, of course, is to exchange y for that inverse notation. So we'll have the inverse of f equals the cubed root of 2x plus 2. Okay, and there you go. So let's take a look at the graph. On this graph, again, we have the original function in black, the inverse in red, and then we can notice again, it's kind of a fun little graph, but they are still symmetric about the line y equals x. So the black graph is going to be our function. It's a cubic function. And then it just gets flipped up over the line y equals x to make that cube root function. So there you go. That's what the graph looks like.